Okay, so our final speaker today is Litany, a senior researcher at NVIDIA and assistant professor at the Technion, where he leads the visual computing and AI lab. So all research focuses on semantic scene understanding and spatiotemporal content generation. Today, our talk titled Data-Driven Simulation for Autonomous Driving. So welcome.
All right, thanks for the introduction. The only thing keeping you from coffee, but luckily I probably like coffee here more than anyone else, so I'll try to keep it brief. Today I'll present IMVC. I think we can all agree simulations are important. We hope simulations can replace us having to risk actual people and instead train and test systems, especially perception systems for autonomous driving, in a safe environment. But usually simulations, they lack in two main aspects. The first is that it's usually difficult to achieve realism. If anyone here worked with Carla, for example, you probably know that there's a serious gap. And scaling them up, in other words, like defining lots of different scenarios usually take a lot of human manual labor. So here I'd like to propose an alternative, which is a data-driven simulation. And the holy grail would be to go out, drive, collect data, and use this data, harness this data to bring that back as a digital twin into a simulation environment. Recently, with the emergence of NERF methods, this seems like a great candidate to take outdoor data, reconstruct it, and bring it back as a digital twin into the computer. But I'd like to highlight two challenges with NERFs. The first is that we are used to think of NERF as the thing here on the left, which is usually there's like NERF excels in situations where there's a centralized object and a lot of different views looking at the object. In fact, that's the only supervision that NERF has in order to reconstruct a decent geometric reconstruction of the underlying scene is by having intersecting rays looking at the same, agreeing or disagreeing on the same color that they're observing. However, in driving scenarios, usually our vehicle moves and gets only a very sparse set of views that it gets to witness the environment. So that's a first challenge. The other challenge is that the scenes are more complex and dynamic. So previous works used tackle this limitation by using additional supervision, either in the form of actual detected boxes or annotated bound boxes or pre-trained scene flow networks. We introduced IMVC, where the task of IMVC is to reconstruct a dynamic driving scene with all the challenges I just mentioned in a scalable fashion, which we achieve by not using any supervision except the input video. And we achieve a higher level of realism. How do we do that? So this is what the output of IMVC looks like. It can be used as a representation, here shown as an occupancy map. And I'll go through the list of how we achieve all the nice properties that IMVC can get with no supervision at all. But before I do that, let me tell you how IMVC works, really briefly. So I'll assume you all know NERF because I don't have time to explain it. But basically, we're using 3 different neural fields, a static one, a dynamic one, and the secret sauce is a flow field, which works jointly with the dynamic field and lets us avoid supervision altogether. How does this work? It wouldn't be a surprise to start with the dynamic field works just as a standard NERF. We take rays that are shot, that we shoot rays from the camera, and we take sampled points along those rays. We plug them into the static field, and we map them to density and color. This is basically NERF. So here I explained it. But our world is dynamic. So what do we do about dynamics? Well, if we just use the static representation, it won't work. Here's a visualization showing why not. So we introduce an additional field. This one is a dynamic field. And the only difference to the static field is that in addition to the input 3D coordinates, we also input a time signature. Great, so is this the solution? Well, kind of. It can memorize very nicely the input, but it won't generalize. And why is that? Because it can easily find the generated solution where each point just takes its own time signature and gets mapped to an individual point in space. So it doesn't have to argue with any, or agree with any other point from any other view direction. And that's how NERF works. So we basically violate the very basic reason why NERF works. So we need a regularizer, which comes in the form of a flow field. So basically, we have this very simple observation that the points we look at a single time, they will move to a different location in space in the next time. So we explicitly model those motions by introducing an additional field. This is a flow field. Again, this is a neural field that gets as input those 3D points, the 3D point coordinates and the time signature of the points we're currently looking at, and it will tell us where those points move to in the next time frame. Now, how do we regularize using this information? We actually force the dynamic field to explain the prediction by taking the combination of the current point we're looking at the current time step and the point in the new location predicted by the flow network. By literally averaging them, we don't allow the neural field to ignore we force a communication between different timestamps at different locations in space. We do this trick for forward in time and also backwards in time, and we take a weighted combination of those of features coming from the present, the one step backwards and one step forwards, and using that weighted aggregation, we push only that combination to the task head, which predicts us the color and density. And that's basically it. That's the whole magic. Here's the full model. I won't go into like other details that were already shown in previous works, like a sky network. It's pretty standard, and a shadow head. It's also pretty standard. I will say that the color is predicted as a combination of the static and dynamic field, as listed here. There's a regularizer here that penalizes the network for using too much of the dynamic field. So basically, we want to avoid a case where the network just chooses to explain the whole scenario through the dynamic field and not just the moving assets. So that's the regularizer. Here at the bottom is the weighted combination that I showed from before. And the very last bottom, I don't have time to go all through the details, but if you can quickly look at it, it's basically telling us that the velocity predicted from the it's a cycle consistency loss on the regularizing that the flow predicted from my current time step, my current location, would be the inverse of the backwards flow predicted if I moved to that new location. Look at this for a second and you'll get it. I'll go through some results. So the first thing we have to do is log replay, where we want to make sure that at least we were able to faithfully reconstruct the original input as it was. We can do that for camera and for LiDAR. A more interesting result is the dynamic static decomposition. So this visualization shows quite nicely how the input video on the top from the actual moving vehicle is being very nicely decoupled into a static scene, and we can clearly see the separated dynamic objects at the bottom row. Because we predict actual flow, we can literally visualize the flow here, not just the segmented RGB of the dynamic field. If you go into our website, you'll see a very nice tool that can let you visualize the flow. So I won't play the whole video here because I don't have time, but feel free to go online and play with this. Just shows the nice separation and capture of the flow. It looks pretty consistent. A nice little nugget that we kind of found along the way when working on this paper is that, well, we didn't want to only have the color reconstruction and geometry reconstruction. We also wanted to get a semantic reconstruction. And this is pretty standard by now in NERF literature, that we can use a foundation model like Dino V1, Dino V2 to render 3D features into, and supervise them with 2D foundational model features like Dino. What we found, interestingly, is those annoying patterns that you see here on the bottom of the screen are inherent to Dino V1 and V2. So this is not our bug, which we thought for a little while there. It's actual contamination into those foundation models that are a result of the positional encoding that they're using. So the network, the output feature memorizes the location of the pixel in the image that it was using, okay, which is sometimes okay, for our case, terrible, because we want to do view consistent reconstruction. So we came up with a very simple trick to get rid of that, basing on the fact that the contamination is a function of the pixel location, not a function of the viewing angle. We basically say that the positional encoding free feature, the one we're interested in, plus a fixed map, 2D map of this contaminating pattern, they should explain the actual foundation model features in 2D. And by doing that, we can get a very clean separation. So if you look at the, here you can see the actual patterns at the bottom row from Dyno V1 and V2, so you can appreciate that they are indeed pixel related. And here at the bottom, at the top part, you can see a video, and on the right, you see what happens if you try to reconstruct semantically with that annoying pattern, and on the left, how cleanly it looks without it. So it was really instrumental for this work to get nice results. Novel view synthesis, that's why we're all here, right? So basically, if you use this method, you can pause the video at some point and then stroll around with a camera, or you can pause in space and let the video keep going from a novel view synthesis. So this is almost a self-contained simulator. We can also, because we can do LiDAR reconstruction, we can also try to emulate different types of LiDARs by densifying LiDAR point clouds. So we can mimic, what would happen had the car driven with a different type of LiDAR mounted on it, which is also very useful for autonomous driving simulation. And finally, we can threshold the density maps and get the occupancy. And because we have this nice semantic features, we can lift those features to 3D and ask the questions like you see in the bottom, like retrieve me all the cars and paint them in blue. And this is what we see here at the bottom. Again, this is by no means real time, so I'm not proposing this is a method of something that can run on the vehicle, but it can perfectly be used as a simulation tool because it can run offline and replace annotations. So thank you for listening. And before you clap, thank you. These are my collaborators, amazing folks. This is my new lab at the Technion, and these are the kinds of topics I'm interested in. So if you're pursuing a PhD or a postdoc, or you just want to collaborate, just shoot me an email. Happy to talk about research in these topics. Thank you.